Hello everyone. In this video we will continue to examine topic 9.5, the Doppler effect, and in particular we will continue to examine the Doppler effect for light waves. So a similar effect occurs for light and other electromagnetic waves. But because the speed of light is measured to be c equals 3 times 10 to the 8th meters per second in all reference frames, the effect is the same, exactly the same, for moving sources and observers. Now, when we do atomic, quantum, and nuclear physics, we will spend a significant amount of time at one point discussing the theory of relativity and what this means. But the heart of the theory of relativity is that light is measured to be moving the same velocity, no matter how fast you are going. And there's a lot more to it than that, but for our purposes, we'll leave it there. If you're curious about this, you can check out that material. So we therefore need to discuss what this will mean. We are going to start with one of the Doppler effect equations, although as it turns out, this effect on the frequency, the Doppler effect on the frequency for light, can be approximated to be the same equation for all cases, with just careful attention to, again, that minus and plus sign. So we're going to start with this formula here. F prime is equal to V over V plus U sub S times F. And we're going to assume that the wave velocity is c, that speed of light. Okay, and we assume that right here, the wave velocity is c equals 3 times 10 to the 8th meters per second, and v is the only velocity in this case that matters, the velocity of the source. So you can think of this as a moving source, stationary observer situation, although as it turns out, our equation will apply for all cases. We then do a little bit of algebra here. So in moving between this step and this step, we simply divide the numerator and denominator of the scaling factor by c. So c divided by c is 1, c divided by c is 1, and then v divided by c is our important parameter. And then we use sort of the first order approximation of the binomial expansion. And I will just defer to your math teachers on that to say that this is, or 1 plus v over c is very close to 1 minus v over c for small v. So v much less than c. That's actually an important assumption being made here. There are cases where objects move close to the speed of light, most of them being particles, so this won't directly apply to them. Then we go ahead and expand. We say that f prime is about equal to f minus f times v over c, and rearrange it. Now, in the version we've been considering, it's almost always been how does f prime depend on f? But for light, the Doppler effect is almost always written in a different way, and this is just convention. But if we drop our f prime down here, we'll see that we can sort of group terms slightly differently, and take f prime and divide by that, take f prime, subtract f, and then divide by that negative f, giving us f minus f prime divided by f is about equal to v divided by c. And this is the version traditionally used in the Doppler effect for light. This is just an algebraic step here, and then this is a small v relative to c assumption. As a result, this is then written as delta f. Notice the delta f obscures which one is bigger, which is useful because we're just going to use the same equation for all cases. And so the shift in the frequency divided by the frequency is proportional to the velocity of the object relative to the speed of light. So the closer v is to the speed of light, the bigger that shift in frequency is. Although this equation is only good for v much smaller than c. So this is our final equation for the Doppler effect for light. It says that the shift in frequency compared to the frequency will be about equal to v divided by c. Now, how do we apply it? Well, we use this equation. We say if the object is coming towards you, then delta F is positive. And we're going to call this phenomenon a blue shift. Blue shift here doesn't mean that the light is blue. It means that the light that is coming at you is more blue than it would have been otherwise. So hopefully you've seen sort of spectra in other classes, hopefully in chemistry. But if not, the big picture idea is that if you take the light from a star or from many other things for that matter, there will be absorption lines, very particular black lines that have to do with particular wavelengths of light being absorbed. And we can tell that those lines are from particular elements, and we'll discuss that more in topic 7. But the general idea is that if this is the light at rest, so this is the light when it's emitted at rest, then if you see those same lines in a different location, sort of in that bluer location, then you know that whatever emitted this light right here is moving towards you. That light is blue shifted because those absorption lines are shifted in the blue direction. And this is what we call the Doppler effect for light. So to back up again, an application in astronomy suggests that stars produce spectra with characteristic absorption lines, and those absorption lines shift based on whether that star is moving towards or away from us. The opposite direction, so if the stars are moving away from us, we will see that their spectrum is red-shifted. And the only reason we get to do this is because we have a good idea of what the light would look like at rest. And so that actually gives us a way to measure the velocity of the stars, which is a pretty cool application. A couple of examples can be found here. You should certainly work your way through them. There are some other applications as well, and I'm just going to point them out here. You can sort of read the following couple of slides, but radar, which is radio detection and ranging, uses the Doppler effect to measure the velocities of different kinds of objects in different circumstances. And it does so by using radio waves. So the Doppler shift is measured for radio waves in order to forecast the weather, in order to keep track of airplanes and other such things. That's a pretty cool application. You should definitely read into it a little bit. Another thing that the Doppler effect can be used to do for light or sound, this one is sound, is it can be used to measure the speed of blood flow. So ultrasound can be used to measure whether blood is at an appropriate speed, and you set it up so that it is measuring the Doppler effect of objects sort of moving inside your body. These are blood cells in this particular case, and you can detect the shift in frequency of the reflected wave, and that gives you an idea of the speed.